So welcome back to your lesson on complex numbers. Here's objective 2, all about plotting those complex numbers in the complex plane and then finding their absolute value, how far away they are from 0. So as I've hinted at before, the complex plane looks kind of like an xy coordinate plane with one little difference here. We'll talk about that in just a little bit. The picture, very pretty picture here, is an example of numbers being plotted in the complex plane. And each one of these numbers are solutions to polynomial equations. And depending on the degree of that polynomial equation, whether it's a squared equation to the third power or the fourth power, that's what color each of those numbers gets. So the number right down here is supposed to be the number 0. Number over here is 1, and up here is I. So any complex number in standard form is written like this: a plus bi. A and b are just real numbers. And notice that that b is being multiplied times some sort of I. The a is the real part of your complex numbers, and your b is the imaginary part of the complex number. Okay? Any real number is also a complex number. Every single real number is also a complex number. That happens when b is equal to 0. So just for example, the number 7, which is a real number, is also a complex number because I can just write it as 7 plus 0i. Okay, for imaginary numbers, we just can't have the b equal to 0. And if the a is equal to 0, then it's a completely pure imaginary number. In other words, something like 7i is a completely imaginary number, pure imaginary number. So we've talked about letters like this meaning the real numbers. There is another letter, a blackboard or double stroke letter for complex numbers, and it looks like this. It looks like a big letter C. We put a double stroke on it. So this means all the complex numbers. Guess how many of them there are? If you answered a whole bunch of them, you're certainly right. Okay, so exercise 7 is about drawing a Venn diagram to represent the set of all complex numbers. And complex numbers also include the real numbers, right? The real numbers are within, they are a subset of them. Now, I'm not actually asking you to draw this. Here's just a picture from your book. Looks like this. Complex numbers are divided up into real numbers and imaginary numbers. All of the real numbers are complex numbers if you say that the imaginary part is just set equal to 0, right? The imaginary numbers, you just can't have b equal to 0. And within that is another subset of the pure imaginary numbers where your a is equal to 0. Whenever you go to graph just a regular real number, it goes on a good old-fashioned one-dimensional number line. But whenever you go to graph a complex number, they're going to go on a two-dimensional coordinate plane called a complex plane. So here's just the number 4, a real number 4 graphed. Okay? So whenever you go to graph a complex number, let's say I wanted to graph 3i, I just make it kind of like a complex plane, or a xy coordinate plane. Okay, so here is the number 4 plus 3i. So instead of this axis here being an x-axis and this axis being a y-axis, what we say instead is the x-axis is for all the real numbers and the y-axis is for all the imaginary numbers. So the number 4 here is just a regular old good old-fashioned real number. 3i is a pure imaginary number. And then 4 plus 3i. So I go over 4 on the real axis, up 3 on the imaginary axis. It's just like graphing a point, an ordered pair. And this one is just an imaginary number with both a real part and an imaginary part. So let's plot each one of these in the complex plane. Actually, I'm going to do the first one with you, pause the video, and do the rest of them yourself and check to see if you got them right. So, I draw myself a nifty complex plane here where this represents all the real numbers, and this all the imaginary numbers. So 4 plus 2i. 4 is the real part, so count over 4 on the real axis, and 2 on the imaginary axis. There's the point 4 plus 2i. Okay, pause it, come back, check to see if you got your answers right. Plotting these numbers on the complex plane, on the same complex plane, here are your answers. Voila. I did them in red this time to make the picture really, really pop. Okay, so we've got -1 on the real axis, up 3i, so -1 plus 3i. Then I've got a pure imaginary number with -4i, just down 4 on the imaginary axis, and then 2 minus 2i, right 2, down 2. It's like the coordinate 2, -2. So I'm going to plot this next complex number, 4 plus 3 on the coordinate plane. Here you go. Like so pretty. Okay, right? 4 real part, 3 imaginary part. How could we find the distance away from the origin? In other words, its absolute value. What do you think? Go ahead. Think about it for a second. If you said the Pythagorean theorem, you're right. Take a look. So you have the distance away from the origin, just makes this diagonal line here, but you can drop that line straight down to the x-axis, or the real axis, and then bring it straight to the origin, and it makes a right triangle. So this is, the real part is 4, and the imaginary part is 3. What's the distance away from 0? This is a Pythagorean triple. It's 5. So the way that we write this is the absolute value of 4 plus 3i is equal to 5. Which is really strange. I mean, you're not used to doing absolute value like that, but that's the way you have to do it for complex numbers. So let me just make a note here that we're using the Pythag theorem. Yes. Okay, so here you go in general. Finding the absolute value of complex numbers, z is equal to a plus bi. A is the real part on the real axis. B is the imaginary part on the imaginary axis. It's just the Pythagorean theorem then. Square root of a squared plus b squared. And we still write absolute value in little absolute value brackets. So let's find the absolute value of a couple of these numbers. Should be pretty easy. Okay, so here I've got the real part, so this is like my A, and my B is actually equal to -12. Okay, so I'm going to put this in Z is equal to, or I should say the absolute value of Z is equal to the square root of 5 squared plus -12 squared. 5 squared, of course, 25. -12 squared is 144. Square root of 169, which I think is 13. Look, we got another whole number there. If you don't know, that's another Pythagorean triple. Let me just write these down for you. Just as a reminder, some Pythag triples. Some of the most common ones. See if you can remember them. We've got 3, 4, 5. We just saw that one. We just saw another one. 5, 12, 13. Can you think of any more? How about 7, 24, 25, and 8, 15, 17. There's tons more of them. That's just the 4 most common ones. Okay, let's look at part 2 here. So here my A is equal to 0 and my B is equal to 17. Of course you don't have to write all this down, but I'm just making sure I show all the steps here. Square root of 0 squared plus 17 squared is equal to, well, this just cancels out, and I've got 17 squared, and taking the square root of that, it's just 17. That should make sense because here you're just going down 17 scratch that. You're going up 17 on the imaginary axis, and its distance away from the origin is a big fat 17, right? Okay, so here's a couple of them for you to try yourself. Pause and do your problems. And we're back. Actually, I'm back from just turning off the sprinkler. I know it's the dead of winter. Why is the sprinkler on? That's because we had some sort of power outage, and it kind of went haywire. Anyway, so here's the answers here on number 1. We got square root of 17. On number 2, I didn't even work it out because I can see it's going to be a 3, 4, 5 right triangle. Ta-da! Absolute value is 5. Number 3, we got square root of 29. And finally, 4, I didn't work out as well because, like we said before, this is just -4 down on the imaginary axis, and it's 4 away from 0. So its absolute value is 4. So that concludes objective 2 on being able to plot complex numbers in the complex plane and finding their absolute value, basically using the Pythagorean theorem. So see you in objective 3.